X3 Cartesian components of a Euclidean vector. A vector is equivalent to an arrow connecting a point to another. So we call this is head and this is tail of an arrow. So A is a point in space, B is another point. So if I use 2 points symbol A and B, then put an arrow on top of them to represent this is a vector connecting 2 points from A to B. So we have a magnitude of a vector and the direction is represented by this arrow. Or simply we write it as a letter that is italic as well as bold. Bold italic letter represents a Euclidean vector. Euclidean vector means this vector is representing an arrow between 2 points in a Euclidean space. The Euclidean space is a space in which Pythagoras theorem works. Later, in the next semester, we study Minkowski space that is defined for the special theory of relativity in which time and space are correlated. For the time being, in this semester, we decouple the time and space, and they are treated to be independent in Newtonian mechanics. Describe the algebraic properties of displacement vector in the figure. A vector is the simplest elementary and fundamental vector we must learn before we study the generic property of a vector. We need to study displacement. Displacement is a vector on a plane or space in actual space. So we draw a parallelogram. Two opposite sides of a parallelogram have equal length and they are parallel. Another pair of parallel sides are A and A. If a vector is the same as another vector, we denote them by the same symbol. And here it is A vector and this is B vector. From this figure, we can see a vector is invariant. It does not change at all under translation. And translation is the change in position, keeping the orientation the same. Okay? Any two parallel vectors of equal length are the same. Okay? These two vectors are the same, and these two vectors are the same. The addition of two vectors can be made by using this method. Let us make the sum of A and B. This is A vector and this is B vector. To make an operation A plus B, we put this A the same invariant and translate B to make its tail overlap with the head of A. In that case, we can find a triangle, this triangle, and The head is connected to the tail, okay? And then when head of a vector is connected to the tail of another, the sum of these two vectors begins with the very end tail and ends at very end of the head. So this is A plus B. In a similar manner, we can define the vector B plus A. In that case, we begin with the B and then add A. So B plus A is here. Elementary school students may know the diagonal of a parallelogram is uniquely defined. There is no other way to represent this diagonal. Therefore, because A plus B represents a diagonal and B plus A represent the same diagonal, therefore, the uniqueness of the diagonal of a parallelogram that we learn states that addition of two vectors is commutative. The sum of two vectors is unique, whether we add in this manner or out of order. Next, we consider the angle between A and B is theta. What is a perp? Where a perp is the perpendicular component of A relative to B. Okay, I have two vectors, A vector and B vector. I'd like to know the perpendicular component of A vector relative to B. A simple way is to put the x-axis along the b-axis and find out the y-axis. This is x-axis, y-axis. It is stated that the angle between the two vectors is a theta. We know that the parallel component is a projection onto the x-axis that is a cosine theta. And what is the perpendicular component? That is the length of this. So this is a sine theta. So a parallel, that is this vector, is called a parallel to B, and a perp is perpendicular to B. The magnitude should be a cosine, and magnitude of the perpendicular component is a sine. And a vector must have the magnitude and the direction. This is a way how to define the direction. Attach a unit vector. Unit means the magnitude is 1. What is the unit vector along this direction? This is called b hat. B hat is nothing but the b vector divided by its own magnitude. So magnitude of the b hat should be 1. So we attach b hat here. We do not know how to write down the unit vector yet, so let us postpone to write in such a manner. Instead, because this vector is a sum of a parallel component, it is called a parallel, and perpendicular component a perp. So because A equals a parallel plus a perp, the way to find out a perp is simply subtract both sides with a parallel. So if I subtract this guy, then it will disappear. So it is nothing but a vector subtracted by a parallel. Okay? So this is a way how to find the perpendicular component. Okay, so a hat is a vector divided by its own magnitude. So magnitude is denoted by the absolute value. And what is the absolute value? Absolute value is the length, and that is the nothing but a vector scalar product with itself. We know A dot B is magnitude product of their magnitude cosine theta. If if I take the scalar product with itself, it is a vector squared cosine 0. And cosine 0 is 1. So a vector absolute value squared. Therefore, what is the absolute value of A? That is nothing but the square root of this. So either we write a dot a square root or square root a squared. So the a squared is the same. They are this, this, and this. They are all the same. In a similar manner, b hat is b divided by its magnitude. Okay, we recall that the magnitude, the a parallel vector, that is the parallel component of A relative to B, that is, what's that? This is A cosine theta and the unit vector along the B direction. We can substitute B hat, this value, for the B hat. So substitute this value in here and there. Square root, square root, square. Then the denominator becomes b squared, and we have a dot b here, and then b again. We can see this guy brings in product of magnitudes and cosine theta, and this one has magnitude of b and unit vector along the b direction. Okay, in the denominator, this guy will cancel, so it reproduces our original result. In addition, a perp and a parallel, they are perpendicular to each other, right? X-axis and y-axis are perpendicular to each other. What is the angle between a perp and a parallel? It is right angle. So cosine right angle, half a pi, is always 0. Therefore, even though I have written complicated calculation, a perp dot a is a perp plus a parallel. So an a perp and a parallel scalar product vanishes. So this value must be the same as a perp squared. So at the end of the day, we find the same result. And you can follow all those calculation. It is a straightforward, looks busy, but straightforward calculation. Okay, number 4, Cartesian basis vectors E1 hat, E2 hat, and E3 hat. They are all, because they have hat. The magnitude of every Cartesian basis vector is 1. In addition, it is unit cube. Length of each side, every side is 1. And the direction of 1, 2, 3, they are all perpendicular to each other. In addition, for example, if I choose E1 and E2, I can make a plane. This, you remember, x-axis, y-axis, and then z-axis. In general, on the plane, on the xy plane, there is a vector that is perpendicular to this xy plane, that is either z-axis or minus z-axis. Our convention to choose 1, 2, 3, the x, y, z-axis is right-handed screw law, and we just follow the way. So forget about this, the other direction, and if you use your right hand, swipe from x-axis to the y-axis, and then your thumb is heading toward the positive z-axis. Okay, that's fine. And then, because they are all perpendicular and because they are all of equal length, the length is 1, scalar product between two Cartesian basis vector is either 1 or 0. 1 if typo, it's wrong. I equals j. It is 1. If I is not equal to j, it is 0. Okay? Wait a second. Let me write it somewhere. Okay. So 1, 1, 2, 2, 3, 3. It's 1. And 1, 2, 2, 3, 3, 1. They are all perpendicular. So cosine theta equals 0. So in a simple manner, we just denote the scalar product between the EI hat and EJ hat to be delta IJ. What's delta IJ? Delta IJ is the ith row and the jth column element of this matrix. We know this is diagonal component. This is 1, 1, 1, 2, ij equal 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. This value is 1 only if it is on the diagonal. They are all vanishing if it is not on the diagonal. These are all zeros. Okay? If the two indices are different, everything is a 0. If the two indices are the same, 1, 1, 2, 2, 3, 3. Only if they are the same, they are 1, 1, 1, 1. Everything else is 0, 0, 0, 0, 0. So we call this one the canonical delta, just to remember the name of this. And what is the delta ij? Just to write down this unit identity matrix, unit matrix or identity matrix, 1, 1, 1, diagonal is 1, 1, 1, and off diagonal are all zeros. This is identity matrix, and delta ij represents 1, 2, 3, 1, 2, 3. 3 by 3 matrix, ij element of the matrix is identical to this scalar product. Describe how to compute the scalar product of two vectors. Okay, Descartes introduced the Cartesian coordinates, and a vector can be expressed as a linear combination of these three basis vectors. The coefficients are called the Cartesian component. And if I take the scalar product, B1, E1, B2, E2, and B3, E3, what happens? Because our multiplication shows that they are always zero except for the diagonal component. So if I multiply this scalar product, we have the three terms and three terms. So 3 by 3, there should be 27 terms in the expansion. However, only 3 among 27 terms, only 3 terms survive. And the survival after this calculation, only 3 terms, 1, 1, 2, 2, 3, 3. Very simple. 3 terms survives. And there is a shorthand to write down this kind of expansion. So using Descartes' Cartesian components, it is very simple to denote them as a form. This is just a copy of the first Cartesian components in a row, and we have a scalar product between A and B. This one stand up. So there's a typo. So 1, B1, B2, and B3. Okay, so we denote this sum by product of these row vector and column vector. A rule of multiplication in here is just by definition the scalar product between A and B. So first, second, third. Multiply, then add them up. In addition, I can insert the identity matrix that we have introduced. What happens? This is the identity matrix. Why don't we multiply this? Multiplication between these two follows the way of multiplying two vectors. First of all, 1, 0, 0, B, okay. B1, B2, B3. What's that? Multiply this first, 1 times B1. Second, 0. Third, 0. So plus 0 plus 0. So this is B1. Aha. If I multiply in here, I would get B1. So A1, A2, A3, we have B1 here. What about this? Multiply this. This, 0, B1 is 0. 1, B2 is B2. And 0, B3 is 0. What about the third row? This one, 0, B1, 0, 0, B2, 0, and 1 times B2 is B3. Aha. So multiplying this identity matrix to this one does not change anything. It is the same. That's the reason why this one is called the identity, multiplicative identity matrix. Just like 1 is a number that is multiplied to another number to generate the same result. So power series expansion of the sinusoidal functions are just memorized. We recall that the e to the x is the sum of x of k divided by k factorial for k runs from 0 to infinity. For any x, this series converges to the exponential function, and we have proved that already in the previous class. And we make an analytic continuation just to replace x with I times x, then still this series is the same, the convergent. And in here, I squared equals minus 1. Therefore, the expansion can be separated into two pieces, a real part that contains cosine and imaginary part that contains a sine. So this is identical to sine of x, cosine x plus I sine of x. It is called the Euler's formula. And the series expansion for the cosine is given here, and the sine is here. If you don't understand, just copy. It is not a mathematics class. So find the derivative of cosine function. If you are well acquainted with some geometric method, then you can compute the derivative of cosine, and you will find this limiting value is 1, and this limiting value is 0. As a result, we can take the cosine's derivative to find to be the minus sign. In a similar manner, sine's derivative becomes a cosine. However, we can still make use of series expansion, and we know this formula, the polynomial's derivative. You know this one very well. If you apply this one to the series expansion of cosine that I wrote here and sine, you can reproduce the result. For example, if I take the derivative and apply this derivative rule for the polynomial function, and the power comes out as a front factor after the derivative, and this power decreases by 1, and 2k cancels the denominators, the 2k in the 2k factorial. And summation runs from, at 0, it becomes a 0. So this summation is over k equals 1 to infinity. I can shift this k by 1, so introducing a new summation dummy variable, j, that equals to k equals to j plus 1, and then j runs from to j 0 to infinity. Finally, this sum is identical to the sine of 2, the negative sign on it. So either way, you just memorized how to compute, or at least just you must know whether you can prove this or not. You must know this formula. Okay? If you don't understand, you don't follow anything about it, so you learn later in mathematics class, but at least a physics class, you must know the answer. Okay?